Hold on, let me record this. So what do you see? A rusty old bicycle, some wood, a wood fence, leaves on this tree. Well, to the untrained eye, yes, that's an old bicycle and a wood fence and some leaves. But to you as chemistry students, you're looking for change. So this bicycle is an example of chemical change going on, which is there's metal in the frame of the bicycle. And you can see the metal used to be gray, even painted over, and some of those parts are rusted. And so there's a color change. There's a little bit of brown in there. There's a little bit of brown in there. When metal rusts, that's an example of a chemical reaction that is a single replacement reaction. So that you can identify by a color change. Now, what else do you see here is some leaves. And so some of these leaves have a little bit of brown in them, a little bit of yellow. So that is a color change. When leaves turn color, there's something going on in the leaf there's chemical reactions that are now different. So anytime you're looking at a color change, you're almost always the background of it is a chemical reaction. Now, sometimes it is food coloring, but for what you see out in nature, if you're paying attention to what's going on out in the world and you see color changes, it's almost always due to a chemical reaction. And so we're going to be looking at the nitty-gritty of single replacement reactions, exactly how to predict the products when you're given two reactants. So the leaf here, you've got this leaf that is the green, red, yellow. When you see a color change, you're looking at a chemical reaction. And here's what we have for today's example of reactions where you'll see big changes immediate. This is a test tube that when I start this reaction, you'll see that this test tube, which is a clear test tube, has a clear liquid at the bottom. That clear liquid at the bottom is not water. And I'm going to add a clear liquid to it from a dropper at the top. And that clear liquid that's being added is also not water. So let me start here with this. So I've got a clear liquid at the bottom and a clear liquid that's being added from the top. You'll see that. And these two clear liquids are examples of what are called aqueous solutions. There's something dissolved in there, and you can't see those ions that are dissolved, but those ions will react. So you've got one solution, reactant. Solution down here is another reactant. Right there, boom, when they meet, there's an immediate chemical reaction, and you can identify that with the color change. And so right there at the interface, when the two reactants meet, this forms a yellow compound that is a solid that you can see is falling down to the bottom of the test tube. That solid is called a precipitate. When it is produced from the chemical reaction and it falls to the bottom of the test tube, it's called a precipitate. Just like rain is called precipitation, a solid that's formed from the reaction that falls to the bottom is called a precipitate. It precipitates by falling down. So you can add more reactant. Slow motion. So you get the general idea that a color change is evidence of a chemical reaction. And this we'll see in reactions today. You're going to be looking at videos where when you mix two things together, you will see an immediate color change or sometimes a color change that takes a little bit of time. And the color changes can be fast, they can be slow, just like leaves changing color or metal rusting. Even though it takes a little bit of time, it's still a color change over time, and that means it's still a chemical reaction. Okay, so I got to get through this before it'll let me go to the next. Okay, so I'm going to switch over to my slides that I can write on to talk more about these redox reactions. Switching over. Okay, and yes, I did see the question that these slides are in 7.0 module. And so because they're review and these are aligned with the lecture from last week, 7.1 lecture. So here we have the chemical reaction that we're going to talk about this week is single replacement reactions. And these single replacement reactions can also be called single displacement. And what is replaced? What is displaced is that one metal will replace another metal. Now, overall, these single replacement reactions are also redox reactions. And in redox reactions, something is oxidized. So I'll say one substance is oxidized. And meanwhile, another different substance is reduced. And so that's what we can see in this diagram is that you've got two substances. One is indicated that's greenish yellow and the other is indicated in purple. They are both reactants, okay? So this is the reactant side or the left side of the reaction arrow. And then over here on the right side of the reaction arrow is the product side. So highlighting the reaction arrow as red. Now, you can think of the chemical reaction as a before and after. So before, you only have reactants. After, you only have products, which means that before, you're never going to have products. And after, you should not have any reactants left over. And so this is the idealized reaction where all the reactants have reacted and you have products at the end. One way to think about this, something that you might have done in your kitchen is, let's say you go to make a sandwich. So you have ingredients to make ham sandwich. Let's say you need bread, you need ham. So those ingredients are your reactants. Bread and your one piece of ham. Now you have your product. They're no longer the individual pieces of bread and ham anymore. It's now called a sandwich, okay? And so even though they started off the parts that are in the finished product, and you can still kind of say, well, it's in there. Well, the goal was to get the sandwich. And so you don't call it the ham and the bread anymore. You call it the sandwich, okay? And so that's what goes on with the overall chemical reactions. You have atoms changing places and bonds formed and new bonds created in the product. And then you have for the redox reaction, the one thing that is oxidized will then be changed and be different. When you see it on the product side here, it is, even though it's the same color, it is the same color, but it has a charge. It has a positive charge. So the thing that is oxidized loses electrons. And those electrons end up being transferred to the substance that gains electrons. So the electrons we can't see being transferred, but what we do see, highlighting this again, is that the substance that is oxidized is now a positive ion. It loses electrons and becomes a positive ion. The substance that is reduced, that goes through the reduction reaction, that gains those electrons. And notice that both of those substances are on the reactant side. Okay, so they're on the left side of the arrow. And so that substance that gains electrons, this purple guy, is picking up electrons from this. The green guy. And then this becomes now, when it gains electrons, a negative charge ion. Okay, now this is in this example, and we'll see by looking at half reactions how you can identify which substance is losing electrons and which is gaining electrons. So that'll be a review too. But in the process of transferring electrons being transferred, there's a movement of electrons. And when there's a movement of electrons, you can get electrical energy. And so this is electrochemistry, the idea that from a chemical reaction, okay, so from a standard chemical reaction, you can get electrical energy. And so that's what batteries are. So batteries are stored chemical energy that are converted to electrical energy because there's a transfer of electrons. There's a flow of electrons. And that flow of electrons, when it's set up to flow through a device, something that you're trying to power, it can be a flashlight, or it can be a small object like a calculator, or it can be a car. When you have the flow of electrons that are the electrons that are being transferred through a device, it will generate electrical energy in that device. So that's a battery as an example of stored energy. So here, zooming in on this lock, is metal rusting. So in this example of metal rusting, you can see a color change. It was gray and it's starting to turn brown. So this is an example of a single replacement reaction, also a redox reaction. So in this, you have iron. So iron is Fe. And the rust is an iron oxide, specifically iron 3 oxide. So that's iron Roman number 3. You're still going to need to know your chemical naming. And the Roman number 3 means that it's the iron +3 ion. Because iron can be +2 or +3, you need the Roman number in there. So we're still going to be using chemical naming, especially this week and next week, in looking at chemical reactants and the reactants and products chemical formulas. Okay, so what you have here in this is looking at the two half reactions from this balanced equation, is that you follow the fate of one substance at a time. So what you have here is the fate of iron. So iron starts off Fe. And on the other side, it is part of this ionic compound. And the ionic compound is Fe +3 and O -2. It's composed of those two ions, and that's that chemical formula Fe2O3. So following the fate of what happens to iron Fe is on the reactant side, it is Fe, but on the product side, it is Fe +3. So this is an example of a reactant that did not have a charge, and then it has a +3 charge. So just like this oxidation kind of cartoon up here, this compound has a positive charge, and that's the thing that is oxidized. And so we can identify that because the charges, the 0 for the Fe is not equal to the +3 charge for the Fe +3 on the other side. The way to make this equal is to add -3. +3 -3 will then be equal to 0. So adding -3 really means that there are 3 electrons that are lost. So E-, remember, is 1 electron, the symbol I use for 1 electron, and it has a -1 charge. When you have 3 electrons means 3 times -1, and that's how it's a -3 worth of charge. And so that has this electrons are on the product side. And when electrons are on the product side of the half reaction, that's the oxidation half reaction. Okay, so iron Fe is oxidized. Following what else is on the reactant side is O2. So O2 starts off O2 on the reactant side, and on the product side becomes O -2 or O -2 or 2-. So that's because it's now part of the ionic compound Fe2O3. And so how is that possible that this is O2 has no charge and it becomes a -2? So it must be that there is 0 is not equal to -2. So in order to make it equal, excuse me, I'm going to have to erase this and move it over a little bit. Okay, moving this over a little bit. So this is O2 and equal to O -2. Filling that in again. Those are the ions that were part of this ionic compound. So how is it that O2 can become O minus 2? Well, it has to pick up 2 electrons. So this is -2 plus the 0 charge. Sorry. Now that's a separate reaction there. -2 plus the 0 charge is the only way this can add up to -2. And so what that means is there must be 2 electrons that are added to that O2 for it to become a negative charge. And so that's what happens in a reduction, is the thing that, going back up to the cartoon up here, the thing that is reduced that goes through the reduction becomes a negative charge because it picks up electrons. Okay, and so this is your reduction half reaction. It follows the fate of one substance. This is O2 is what is reduced, compared to the oxidation half reaction was Fe is oxidized. Okay. Okay, so that should feel like, okay, review, I got that. So let's take a look at the metal activity series. So for the metal activity series, you just need to know how to use this to predict the single replacement reactions. Is there going to be a replacement? And that is, will one metal replace another metal? And that will happen if one metal is higher. So the higher metal is more reactive and it will replace a lower, less reactive metal. So that's why these are listed as a column, as a vertical column. These metals at the top are more reactive. They have higher activity compared to the metals down below. As you go successively down, these are less reactive. So a higher metal will always replace a lower metal, and there will be a replacement reaction. And that is part one. Okay, now it does not always happen that there's a replacement, because the metal that is more reactive, the metal alone is the more reactive metal. Okay, if the metal that is part of a compound is more reactive, then there won't be a replacement. And I'll show you that in the next slide. But first, this activity series you use to predict replacement. Which metal is higher will replace. The second part is equally as important. So you need this for two parts. You also need this to predict the ion that forms. Okay, so if you do predict there is going to be a replacement, so you have this column. The other side of this column is equally as important, and this is the ion that is formed. Okay, and so the ions that are formed are indicated on this activity series only for some of the metals. Why? Because the other metals you can predict using the activity series with the ion formed by the family number. So the family number, if it's 1A, 2A, or 3A, will tell you if it's the ion charge +1, +2, or +3. So use the family number from the periodic table. Okay, so I need my periodic table. Here's my periodic table that is with those element symbols, and I can add the ion that's formed by looking for lithium. Lithium is in family 1A, so it forms the lithium +1 ion. Potassium is also in that family, and so is sodium. So I can list all of those as the +1 ions. So that's K+ and Na+. This is calcium. So calcium is in family 2A. So that forms the +2 ion. So that's Ca+2. And magnesium is also in family 2A, and that's +2. Aluminum is over in family 3A, and that is meaning that it'll be aluminum +3. So these metals, why are the metals listed here? Zinc, chromium, iron. These are metals that you can't predict using the family number because they're in the B series. They're in the middle, the transition, or they're below the stair-step line. So you have a few more of these that the only one that we actually do work with is the nickel, and I'll add that. Nickel becomes a +2 ion, or 2+. I also want to point out this is H, or hydrogen, is also on the activity series. it's written as H2, but it can appear as a reactant as just H. And it is the one gas that appears on the activity series because hydrogen can act like a metal when it's listed in family 1A. It can lose one electron and become the +1 ion. Okay. But when hydrogen is an element on its own, it will never just be the hydrogen atom. It will always be written as H2, and we'll see some examples of that. So these other metals, the cadmium, the mercury and gold, we don't need to worry about those ions that are formed. We won't be seeing those. Okay, so that should be a good review of your activity series. And we're going to use that activity series to predict the metals, one metal replacing another. So here's the general format of the single replacement reaction, is that you have the one element that is a metal alone. So this is a metal alone. And then you have an ionic compound. So for this ionic compound, there is a metal in that ionic compound. The metal in that ionic compound is B, because the metal is always listed first in the ionic compound. The metal cation, which is a positive charge, okay, is part of that ionic compound. And the other part of that ionic compound is the anion, that's C, with the negative charge. So the positive charge is always listed first, or the metal, because the metal is always the cation, is always listed first in the ionic compound. You don't see the plus and minus signs in the ionic compound because the plus and minus signs are when you have the crossover rule, you only have subscripts and no plus and minus signs. Okay, and so using the activity series to predict if the replacement will occur, if A is more reactive. Okay, so let me put the if. If A is more reactive, it will form an ion. Okay, and then it will replace the other metal, the lower metal B, in an ionic compound. And so the process of writing the ionic compound chemical formula is to write the ions with the charge values and then use the crossover rule, which is to say, don't just connect or write A and C next to each other. What you have to do is write A as the ion A+. Okay, so how do you know what ion forms from A? Well, that's going back to the activity series. That's this column that we use there. Okay, so if A is lithium, it'll be +1. But if your metal alone is aluminum, then it forms a +3 ion. So make sure you go back and use that column. And this going to here is that A forms the ion, and then it will bond with, the only thing it can bond with is the negative charge, the anion C. So that is writing the ions with the charge values and then use the crossover rule to get the new ionic compound chemical formula. So this is your new ionic compound. Meanwhile, the other metal that is left out on its own, well, then it becomes a new metal alone. Or we'll also see a new gas that is formed. Okay, so I'll show you those examples. But this replacement reaction only happens if this metal alone is the more reactive metal. Because if A is less reactive, and that means it is lower on the activity series, it will not replace B. Okay, so this metal alone has to be more reactive. If B, this is also a different way of saying this, if B is more reactive than A, if the metal in the ionic compound is more reactive, it'll just stay in the ionic compound. And so what you will see is no reaction. That's an example of no reaction occurs. Okay, so, oops, I got to erase my Okay, now let's write this example. So here's an actual example where you have two reactants and you want to compare those two metals. So you've got copper. Oops. Okay, so you've got copper compared to silver. So use the activity series and find which one is the higher metal. So on the activity series, you look for copper and silver, and you find that copper is higher. And copper is higher, it's more reactive, and it will replace the silver. Okay. And so this means, though, that you don't just connect the copper to the nitrate, that's NO3. What you do is you need to write the ions. So what's the ion that copper forms? So going back to the activity series, the ion formed from copper is this +2 ion. Okay, so copper forms the +2 ion. And so we want to go back to write that ion that forms. And so this is the copper +2 ion, and it will bond with not NO3, but the ion NO3, which is NO3 minus. That's the nitrate ion. Then you want to use the crossover rule to write that chemical formula. So that's going to be CuNO3 in parentheses, and then a subscript 2 outside of the parentheses. And so it's not, you should notice, just connecting Cu to NO3. Okay, so it is not, the product is not just writing those two parts next to each other. Oops, sorry. So this is one product, CuNO3. And then the other product you have is, don't ignore the part that the silver is left on its own. So the other thing is that you did have silver, and that will be written as an element without a charge value. So even though silver did start out the +1 ion, it ends up just being not an ion, just being no charge value. So no plus or minus sign. And this is an example of a new metal that's formed, and this is called a metallic deposit. This is when you have on the product side a metal that is a metal alone that wasn't there before. Okay. You would also want to balance this using coefficients. So I would actually put a 2 here and then need a 2 there. So we're going to do all those steps. Okay. So here's this example of what happens when you see a single replacement reaction where you have replacement going on and you see a new product that's a metallic deposit. So hold on. Okay, so the metallic deposit, when your product, on the product side, you have a metal that was not there before. I think I need to switch to the other version of this. Hold on. Okay, let me find the PowerPoint. Okay, do you guys see the single replacement reactions on the screen now?
Yes.
Okay, good. All right, so when you have the products of a single replacement reaction, when there is a replacement, this is the metallic deposit. And so here's the example that we just wrote the chemical formula. When you have copper and silver nitrate, this starts off, let me show you here. The piece of copper is this brownish wire. And then the silver nitrate is a solution that looks like water. It is silver nitrate aqueous ions of silver and ions of nitrate, and they're in this solution. Okay. And so this is the beginning. Those are your two reactants, copper and silver nitrate. So right away, you can see a little bit of change. And over time, this change becomes more prominent, is that you got kind of a black fuzziness. And so that's one thing to remember. Even though some of these reactions take more time, it's not an immediate color change. When you see a little bit of change, that means there's a reaction going on. Even if you sense, is this a little bit of change? It's a change. That's a chemical reaction. So here you've got, this is developing kind of a fuzziness. That is a color change. It's not that brown wire anymore. And it's a fuzziness that's black and now it's gray. Well, what is that fuzziness? That is the formation of silver. And we had just seen that silver is a metallic deposit. It's a new solid that's formed. It wasn't there before, and it's there now. And so you could eventually just basically all of this brown copper will be gone, and you will only have this brownish, grayish fuzz. And you can also see that the solution is turning kind of bluish. That also was not there before. And that's the solution of copper nitrate that's on the products, has a bluish tint to it. Okay. But let's take a look at another possibility when the new product that formed is a gas. And so this can happen when your product is hydrogen. So hydrogen H2 is a gas. And when you have a gas that's a product, that will appear as bubbles. So in this example, this is mixing zinc and hydrochloric acid. So showing you this. The starting point is this liquid at the bottom is hydrochloric acid. It looks like water, but it's not water. It has ions in it, hydrogen ions and chloride ions. And then I'm going to drop in a piece of zinc, which is a grayish, silverish piece of metal. Okay. And so right there, those are the two reactants. Hydrochloric acid is the liquid and zinc is the solid. Well, what do you see immediately is some bubbles. And that's not from mixing it. Those bubbles are the product. And so when you see bubbles, that's an indication of a formation of a gas. And the gas that's formed is hydrogen gas. Okay. And so we could do this by writing out the products, doing the crossover rule. But this hydrogen gas is something that you'll see in these reactions today, is that you can test this gas that's formed. And you're going to see this here in this video. The gas that's formed is odorless, it's colorless. And basically, if you put a little cap on the top of this test tube, you're going to collect the gas in the test tube. And so let me speed this up. I think this is going to test this here. You can test the hydrogen gas by putting a match to it, and hydrogen gas makes a sound when it combusts. I'll show you that again. So hydrogen gas can be tested because the combustion of hydrogen gas, when you burn hydrogen gas, it makes a sound. So collecting the hydrogen gas, can't see it, but you can test for it. There you go. Okay. So you also will see single replacement reactions where there's no reaction. So that was when the metal alone is less reactive. So when that metal alone is less reactive than the metal in the ionic compound, there's not going to be any replacement. And so what happens when you have no reaction is you don't see any change. So let's look at this. In this reaction, you start with a test tube and you add this clear solution that looks like water. That clear solution is zinc nitrate. It looks like water, but it's not water. There's zinc ions and there's nitrate ions that are dissolved in there. You add a piece of copper, which is that brownish solid in there, and you see those two reactants. You wait and you wait and you wait, and you keep on waiting, and you still see those two reactants. So unlike the first reaction where the copper started to turn kind of blackish, fuzzy-ish, that's not happening here. Okay. So that is the example of no reaction. You don't see any change. So no change for no reaction. Okay. So here I'm going to go back to my slide so I can write on this. Okay, so I've got all right. So when you have a single replacement, you have a metal replacing another metal, and that metal has to form an ion. Okay, and so you use the activity series for both of those. Well, then you write the ionic compound, and this is writing the ions and using the crossover rule. Whoops. Okay, so the new ionic compound and the new elements are an example of a metallic deposit reaction or where you have bubbles formed. And so you're going to see both of these in the examples today in the lab. So let's actually go to the lab procedure. Let me find that and work on that exact example. Okay, so here in this procedure, we talked about single replacement reactions. And in this, we've got, moving down onto here, the activity series, you have all of those ions in there. And I want to go to this example here. So let's work out this example. So this is the stepwise process. When you are given two reactants, you never actually have to guess what the reactants are. You're always going to be given those reactants. But one thing to point out for this lab is that the name sulfuric acid, you won't know how to write the chemical formula. Okay. And so that's because we haven't learned to write those acid chemical formulas yet. So what I'm pointing out to here is on this, you have the names of acids: hydrochloric acid, sulfuric acid, nitric acid, and acetic acid. And you have those chemical formulas given to you here. I also want to write the ions because you will need the ions for these acids. So this is H plus and Cl minus. This is H plus and SO4 minus 2 charge. That you should recognize is the sulfate ion from your polyatomic ions list. This is HNO3, so this is H plus and NO3 minus. And then you got, this is acetic acid, which comes from the acetate ion. H plus is the cation, and C2H3O2. That's the hardest of the polyatomic ions, I think. And it has a negative charge. That's called the acetate ion. Okay, so I'll write that if you remember that, acetate ion. And so you need these ions because when you are writing the ions to predict the new product, you need to write the ions and use the crossover rule. So you have the sulfuric acid chemical formula, which is H2SO4. Okay, so you want to have these two reactants, which are zinc and sulfuric acid, and write those reactants chemical formulas is the first box. So the chemical formula for zinc is the element symbol for zinc, Zn. And then sulfuric acid you have from the list down below, which is H2SO4. So the next thing you want to do is then use the activity series to compare two metals. So the comparing the two metals are the zinc compared to the hydrogen. Okay, so zinc and hydrogen, that's H2 and H2SO4. So looking for the zinc and hydrogen, I see there's zinc is here and the hydrogen's down here. So this zinc is higher. And if zinc is the metal alone, which it is, it will replace. Okay, so zinc is more reactive because it is higher and it will replace the hydrogen. So let's do this, which says underline the more reactive metal. So the zinc is the more reactive. So all I have to do is underline it. So if there is a reaction that will occur, and this will occur because zinc is more reactive and it's also the metal alone, then you want to predict the ion that's formed. Okay. Now it's not always going to be that the metal alone is more reactive. So if it's not, then that would be the no reaction. Here's the box where you would explain why. But this is, so zinc forms the ion. Let's take a look. That is +2. So zinc forms the +2 ion. Okay. So to figure out the chemical formula, we need the ions for H2SO4. We need the ions for the ionic compound, which are H plus and SO4 minus 2. How do I have those ions? We wrote them here, remember? So you need the ion for zinc will combine with, oops, I wanted blue here. So Zn, the ion for zinc, will combine with the anion. It'll take away this ion from the the hydrogen. It will replace the hydrogen by taking away its ion and form a new ionic compound. So writing this chemical formula, it would be Zn2 and then SO4 2. Because you can divide both of those subscripts by 2, this will be Zn1 and SO4 1. And because you can get rid of ones, this would be ZnSO4. And when there's no number outside of the parentheses, you can get rid of the parentheses. So this would be the correct chemical formula of that product. You also have, the other part of it is that you have, actually, let me move this over. You also have that hydrogen was there. So you also have the hydrogen ion. Now, what happens to the hydrogen ion? Well, it's not left out in the dark on its own. It will revert to no ion. It's not going to be an ion anymore when it's on its own. And when hydrogen is on its own, it is actually not just hydrogen, it is always H2. Okay, so that would be the other product, is it's not H plus, it's not H, but hydrogen, when it's on its own, will always find another hydrogen, and it will be the diatomic molecular element H2. So your element, the names of those products are hydrogen, that's H2, and the name of ZnSO4. Well, you have the chemical names for those products. This is a reminder, step 5, is that you need to remember the stock system. You need to remember to use the Roman number when you have metals that have more than one charge. That's for copper, chromium, iron, lead, or tin. Okay, zinc is not one of them. So when you're writing the name for zinc, you don't need a Roman number. You just need the name zinc. And then you need the name of that SO4, that's the polyatomic ion sulfate. Okay. But for the balanced chemical equation, sorry, I skipped that step. That was step 4. You need to write the chemical formulas of the reactants. And that comes from this first box. Okay, so that is Zn plus H2SO4. Now, it doesn't matter which order. I could write Zn first, or I could write H2SO4 first. What matters is that they are on the left side of the reaction arrow. Then I've got a reaction arrow. And on the right side, I have the products. And so the products chemical formulas are going to come from the finished, the end, what you've crossed over and down and reduced. So that's going to be the ZnSO4 and H2. And again, the order doesn't matter. I could write H2 first or SO4, ZnSO4 first. They just have to be on the right side. Okay. So then you want to balance it. And balancing it is making sure that all the atoms are equal, and this looks like it is balanced. And so you will see step 6, which is observations. Actually, you're going to make all the predictions first before the observations. So making all those predictions first before going on to observations is the goal. This is here. Let me go to the lab report page. Okay, so the lab report page. Okay, so here's your lab report page. These are the exact same boxes. So it's that you have different reactants now. You have zinc metal and hydrochloric acid. You have copper metal and silver nitrate. So you have 1, 2, 3, 4, 5. And for these in part A, you want to fill out all the boxes except for the observations. So basically, this first one, you will be doing, I want to move this down. You'll be filling out all these boxes and then save that last box. So these boxes, reactants, chemical formulas, comparing two metals, write the ion that's formed. If there's a reaction, the products, chemical formulas, chemical names, and the equation. Okay, and so you have those steps in the procedure to follow. You have the activity series, you have the metals that need the Roman numbers. So follow that example and use that. It's page 3 of the procedure. Okay, so what I'm going to do is resume recording. So this is an example of a replacement reaction, number 1, and number 2 is an example of no reaction. And so you will see this in the videos, okay? And so the goal is to now take a look at those, the videos. So let me show you where you can find that. It's on the lab submission page. So that's going back to here. Okay, so when you are in the lab page, okay, so first let's find the lab page. So this is in module 7, single replacement reactions. So this is the lab page. On the lab report submission page, so clicking on here, this is where you will find all of the experiment videos. So you have the predictions for those 5 experiments, and these are the videos, the experimental results. Here's the observations. So you have 1, 2, 3, 4, 5. You have 5 videos, and you will then put in the observation section of your lab report what you see. And so that's doesn't have to be detailed, just has to be what you see. Saw bubbles, saw color change, and it should be aligned with what you predicted, that you were going to have a metallic deposit or a gas formed. Okay, so so in the single replacement reactions, I talked about how they're also redox reactions, and redox reactions are important in batteries, which is a chemical energy stored in the battery is converted into and becomes electrical energy, and that's the electrochemistry. So the idea of a redox reaction is in your lab procedure. This is a review of redox reactions. And so oxidation is when you have a substance that loses electrons. So that's oxidation is loss, that's oil. And then when you have a substance that gains electrons, so the substance that gains electrons, that's reduction. So that's oil, Rig is the mnemonic. Oxidation is loss, so oxidation is loss. And reduction is gain is Rig. Reduction is gain. So you have that here. Oxidation is loss and reduction is gain. But the way you can determine what's losing electrons and what's gaining electrons, what substance is being oxidized compared to what substance is being reduced, you do that by looking at the half reactions. So remember, we did that in the slides earlier. So when you are given a complete balanced equation like this one with the magnesium and the aluminum chloride, you want to follow the fate of one substance. So this is magnesium, and then magnesium becomes part of this ionic compound, magnesium chloride. So what that means is that this is ions. It is the magnesium ion +2 and the chloride ion minus. And so this is the 2 half reactions are following the fate of the substances that change. So the first one is magnesium becomes magnesium ion. And so this has magnesium with no charge, then on the other side becoming magnesium with a +2 charge. So the only way that can happen is if that magnesium element with no charge also has lost 2 electrons. So that is, you can follow that with the charge values. Let me zoom in. Is because 0 magnesium and then the magnesium ion is not equal to +2, I have to add to -2. So that means -2 is adding 2 electrons. And so I added 2 electrons to the product side. Okay, and that was in order to balance those charges. Okay, and so we can see following the fate of the aluminum. So aluminum starts off in the ionic compound AlCl3. So aluminum is the ion Al +3. And there's also the chloride ion. Now you should notice that the chloride ion doesn't change. It's Cl- before and it's Cl- afterwards. But the aluminum does change. It's Al +3 ion before, and then it's aluminum with no charge after. And so this other half reaction we're following the fate of this aluminum. It's the +3 ion. So let's write that +3. And then afterwards, it's an aluminum with no charge. So since +3 does not equal 0, this, in order to get this to equal, +3 will need to add -3. And so here that -3 means that I added 3 electrons to the reactant side. And that was, again, to balance those charges. Okay, and so when you have the electrons on the product side, this is an example of oxidation. Okay, this is magnesium is the thing that is oxidized. This magnesium Mg, which is in the reactant, so magnesium is oxidized. And then the aluminum that is the ion, Al +3. So this is aluminum +3 ion is what is reduced. So the aluminum atom in the aluminum chloride is reduced. And so this is Al, let's actually write this here, as that this is what is reduced, is this entire compound, AlCl3, is what is reduced because aluminum is part of that whole compound. So what you would write here is that AlCl3 is reduced. Why isn't it just aluminum? Well, first of all, it's not aluminum because aluminum Al is on the product side. The things that are oxidized and reduced are always going to be on the reactant side because remember, products are different, right? So this is aluminum that is part of, so it's the ion that is part of this compound. So you say that the entire compound is what is reduced because it's part of the compound, the aluminum ion. Okay, so what happens in a redox reaction is a transfer of electrons. So it's a transfer of electrons that occurs. And so the substance that loses electrons, this magnesium, it loses 2 electrons. And it loses 2 electrons times as much magnesium there is. So 2, then another 2, then another 2. It can keep losing electrons. And then what happens is those electrons are picked up by this aluminum ion. And this picks up 3 at a time. So in order to balance those numbers out, you'd have to like add coefficients of how many were lost and gained. But overall, one substance is losing electrons and the other substance is gaining electrons, and that represents electrons moving. So when you have electrons transferring from one substance to another and you have them separated like in 2 beakers, that will be a flow of electrons. And when you can separate them through a wire, that will represent electrical energy. That's a movement of electrons through a wire is going to be electricity. Okay, and so that's the electrical current that we can generate in a lab from the 2 beakers, and that we saw as a worksheet example, which was the electrochemical cell, also called the voltaic cell or galvanic cell, but it is roughly what's going on inside of a battery. Okay, and so batteries are super important. Batteries are stored energy. And you can have a small battery, you can have a larger battery. Now there are batteries for cars, and that's great because we need to start moving away from fossil fuels and moving into stored energy that we might have gotten from, say, solar power or wind power that you can store as chemical energy in a battery and then use it to power your car or your refrigerator or anything. Okay, and so this is the salt bridge and the electrodes. We're going to take a look at that. Let me find that on the, I think it's in the lab report. So let me take a look at this on the lab report. Okay, so in your lab report, you've gone through part A. That's good. And then you have part B. So part B is that salt bridge battery. And you need to take those voltage measurements. So the voltage measurements are going to be from videos that are on the lab submission page. So let me find that and show you. It is, okay, so here's your lab submission page. Where is it? No, here we go. Okay. So on this page, you've got the part A, and then for part B, you have the voltage measurements for these two. So you're going to need to watch the videos and pause the videos to write down those voltage measurements.